Hello everyone, I am Selim Buket Aydoğdu and I will try to answer the questions that have been asked in the fourth homework about structure and operation of a DC machine in the context of electromechanical energy conversion 1 course. In the first question, I would like to talk about the construction of a DC machine. Here we can see the housing of a DC machine. It is of course stationary. We can see the field winding and pole piece of the DC machine, and we can see the armature of the DC machine. I would firstly talk about the stator of the DC machines. The stator of the DC machines has poles. As we can see here, we have 2 poles. The poles are excited by a DC current to produce a magnetic field inside the machine. And the armature is any moving part of an electrical machine. We have an example of an armature here. This is the part that a voltage can be induced by a magnetic field. As we can see here, the number of the windings of armature is increased. This helps the machine to rotate continuously. Stator is a stationary part, and the armature is a rotating part. And then we have the rotor. The rotor is the dark gray part of the DC machine. The rotor has a ring-shaped laminated iron core with slots. And we have the commutator, the golden colored part with some air gaps, and we have the black and yellow part as our brush, and we will talk about these two in a minute. And of course, rotor is the rotating part of the DC machine. In the second question, we are asked that define and explain the electromagnetic forces acting in DC machine. I would like to show the field winding. Firstly, the green parts are these parts in this picture in 3D modeling, and these yellow arrows are representing the magnetic field in the DC machine thanks to the stator of the DC machine. This magnetic field is directed from the North Pole to the South Pole, and we have actually this armature here which carries a current, and this when electric current passes through a coil in a magnetic field, the magnetic force produces a torque which turns this DC motor, and actually this is the Lorentz torque only. And if we apply the right hand rule, but before let me draw the XYZ plane. Let's say it's X, Y, and Z. We have this rotor placed like this. We have a current inward here. Let's say it's in the Z direction. Our current is in the Z direction. Our magnetic field is in the -Y direction. And if we place our 4 fingers in the current direction, and if we bend our fingers through the magnetic field in -Y direction, our thumb will show us our force direction. So that we have a force direction in the -X direction, and we already have a magnetic field in the -Y direction. We already have a current direction in the Z direction, and of course, lastly, we will have the F tangential, the component of force, F tangential here. In the third question, we are asked to explain the role of commutator and the brushes. We have the stator here, North Pole and South Pole, and we have a magnetic field here. And we have the electromagnet that is caused by the winding which carries a current. We have if we don't switch the wires here, we will our electromagnet will line up and it will be stable at this point. However, if we switch the wires, the north pole and, as we can see, north pole and south pole will replace, and our electromagnet will rotate continuously. And instead of doing this manually by switching wires, we have the commutator. This commutator is a rotating part that has air gap in it. And we have brushes. We have brushes which are stationary parts. When let's say our current is in the way that it's going like this, just like here, it's going like this. When the brushes are go through an air gap, this current will change its direction, and so that our electromagnet will continue to rotate instead of switching them. And also these brushes have springs in it, so that they can protect their stationary status. In the fourth question, we have the simplest equivalent circuit of a DC machine. We have the armature, the rotating part of the circuit, and the field part of the circuit. And if we have a bigger terminal voltage than EA, the back EMF, it will represent a DC motor. And if we have smaller value of terminal voltage, we will have a DC generator, and the armature current will be in this direction. This purple graph represents the space distribution of air gap flux density. And if we would like to calculate the flux, average flux per pole, we can calculate it as this. It is the integral of B times dA. It will be equal to 0 to L, the length of the air gap here, 0 to pi, since one pole spans 180 degree electrical in space. B max times sin theta. This will give the B, and R times d theta dl. R is the radius, radius of there. So that we will end up as minus B max times R times L times cos theta 0 to pi, and phi will be 2B times B max times R. Okay, we find the phi max, and we know that we can calculate the EMF from this phi function, and we ended up with E max, the maximum EMF value, n times 2 times B max times R times L times omega mechanical times sin theta. This theta is replaced with omega mechanical times T. Omega mechanical is the shaft speed in radian per second. And we want to calculate the average EMF value, since we are dealing with DC values. And we will end up 2 over pi times n times phi max times omega mechanical, and we call this part Ka times phi maximum. Ka is the constant of the armature, and we have a induced voltage, EMF voltage, is equal to Ka times phi max times omega mechanical, and we can find the torque from the power statement. The electromagnetic power will be equal to from here, VA times IA minus IA square times RA, as we can see here, VA times IA minus IA square times RA will be equal to EA times armature current. So that we can replace with the multiplication of torque times the shaft speed, and we will end up with the torque formula of Ka times phi max times Ia. In this very last question, we are asked to explain the power flow in generating and motoring modes of DC machines. We have the equivalent circuit here to help us. I would like to first talk about the losses in DC machines. We have mechanical losses. The first one is bearing losses. Because of this bearing, the balls will have a friction loss as the shaft rotates. And then we have the windage losses because of the air friction as it rotates. We have magnetic losses. We already know them, eddy and hysteresis losses. And we have the copper losses. These copper losses sourced by the armature resistance and the field resistance. However, if we create a field by a permanent magnet, this field current will be 0, so that we can ignore IF square times RF part of the copper losses. Okay, after this we can continue with the power flow of motoring. As we know, in motoring mode we convert the electrical power input to the mechanical power output. So that first we have an electrical power input, hence we will have losses in electrical system, and we will have losses in magnetic system. And at this point we will reach the electromagnetic power. After that, we will have losses in mechanical system. Eventually, we will reach the output power of the mechanical system. However, in the generating process, we will convert the mechanical input power to the electrical output power, so that we will firstly input power of mechanical, and then we will have mechanical losses, and we will reach the electromagnetic power. Hence we will have magnetic losses, and after we have magnetic and electrical losses, eventually we will reach the electrical output power. So as we can see here, electromagnetic power is higher than mechanical power in the motoring mode, and electromagnetic power is less than the mechanical input power in the generating mode. And these were all my answers.